Hello, everybody, and welcome to the 8th session of ShareIT Italy. My name is Matteo Di Tucci. I am a developer here in ThoughtWorks Italy. And before passing the mic to Anupriya Rahul, I'll just spend a couple of minutes to briefly introduce what ShareIT is, and also to briefly talk about the code of conduct for today. So this series of events has been organized by a company called ThoughtWorks, which is a global consultancy firm. We have offices across all the world, and specifically here in Italy, we are based in Milan, even if many of us live in different parts of the country. For instance, I'm currently based in Florence. Knowledge sharing in ThoughtWorks is very, very important, both internally and externally. I'm saying this because you might have come across ThoughtWorks because you've read a book written by a thought worker, or from time to time, you might have read an article from the Martin Fowler blog, or came across the Tech Radar initiative, which is among one of the most popular from ThoughtWorks. Zooming in specifically into ShareIT, we are an Italian tech community looking to share their experience with the rest of the world. The mission that we gave to ourselves is to empower individuals and organizations. And in concrete, the first objective we are trying to pursue is to contribute to the community by sharing what have been done and seen in the recent past. In concrete, what we have been doing is organizing this series of events. Usually we talk about tech, but sometimes also about ways of working, and not least diversity and inclusion, which is a topic very dear to many of us. Last slide from my side, and this time is instead around code of conduct. So sure, in a nutshell, the rule of thumb is just to be kind with each other, but I wanted to do 2 remarks. The first one is that today the audience is very big and also a little bit varied, which means there might be people with, 30 years of working experience, and then other people who are instead just approaching the tech industry. So let's keep this in mind when we talk with each other inside the chat. And in general, let's try to be teachers and learners with everybody else. The second remark I wanted to make is that we definitely believe that the knowledge sharing is definitely going to come from Anupriya and Rahul, but also we put a lot of value in the conversation that happens in the chat. So please ask all the questions, don't be shy about it. Tell us what's your opinion, what has been your experience in the past, so we can try to enrich each other also in the chat. But again, try to be respectful as much as possible. Specifically in terms of questions, the mechanics works like this. Whenever you want to ask a question, just type it here in the chat. And then me and Ronnie, who is also facilitating today's session, will collect this question and ask them to Rahul and Anupriya. Specifically, there will be 2, let's say, moments where we're going to ask questions. The first one will be roughly around the middle of the talk, and then the rest of them at the end of it. But in a nutshell, whenever we have a question, just type it here, and then we're going to take care of organizing them and ask them to the speakers. With that being said, I'll shut up and pass the mic to Anupriya and Rahul. Thank you.
Thank you. I'll share my screen. Hopefully my arrangement isn't too messed up. That and this. Could you confirm you're seeing the screen correctly? Right?
Yes. Yep.
All right. So continuing on from ShareIT, I think this is our first time here, right, Anu? So hopefully we can make it worth it as well. Right. So welcome to the talk here. And this is mostly or probably a too much details talk. And I'm very appreciative of the fact that a lot of people have taken the time to come to a talk about too much details. So whenever you want to say too much details, just say it out. But then also, we are here to learn about the too much details, right? But before that, Anu here has a story to share.
Hello, everyone. I'm Anupriya, and this is me doing underwater diving in Portugal. And when I was doing this, I was able to experience this beautiful world of the underwaters. I really love the creatures, the plants that I was able to see. And I have a dream. And the dream is that the future generations are able to experience this wonderful thing which I experienced, and they're able to relish this beautiful world of flora and fauna inside the water. But there is a bit of a problem here. The problem is some companies, they use the water near the poles to cool down their data centers. And actually, this is good because they're not using any external source. But because of this, what happens is the temperature near the poles rise, and then the polar ice caps are melting. Because of which, what happens is a lot of flora and fauna, which only exists at certain depths with certain temperature, is not able to live, and therefore they are all being lost, and maybe the future generations won't be able to see this. Now, my question is, what can we as software developers do to make the world such as the future generations can also enjoy the experience that I had? So,
yeah. Right. So that seems to be like a tall claim that we want to do. And then let's see how we can go do it. And before that, we can talk a bit more about ourselves. I'll start with me, I guess. So I'm Rahul, go by Lispy Clouds on the internet, do a lot of stuff, mainly coming in from the infrastructure, site reliability engineering, that kind of background, write a lot of code, but that's platform code, and see the JVM running in very different contexts. Probably not so much so at feature delivery, but have used it in very weird stuff. But yeah, I have a, how do you say, on and off relationship with ThoughtWorks. I've been there twice, not there currently, but I don't know what the future holds again. So, but I still have the ThoughtWorks merchandise here, right? So I'm currently based out of London, and Anupriya here probably has a slightly different experience in mind, but I'm not sure how much of it she actually wants to remember.
Okay, so hello, I'm Anupriya. I'm currently with ThoughtWorks. I'm working at London. I worked with Java for quite a while now, and I worked in Java back as Java 6 in some of the core environments such as banking. And first I thought that I understood Java, but now I think I understood the IntelliJ debug pointers more. So while we are going through the talk, we'll also be sharing some of the newer features that are coming through. And the whole talk will be focused on how can we create better code so that we can help in keeping the temperatures of the ocean less by emitting less heat, right? So let's go on a journey in both tech and places. And to understand how we can make this a major impact, let's try to understand what is the highest percentage of language which we can actually work on to make an impact.
Right. So maybe we can go on like seeing what the current state is. So clearly Java or the JVM based languages, they enjoy a quite a fat market share here. And that's probably employing a lot of us in this talk. And probably that's why most of you are here as well. Given that, and probably the inefficient code that we're writing, that seems to be the source of all the global warming or some of the global warming. So, and a lot of us maybe have seen this thing, right? I think whoever is old enough to install Java back then have seen this device. I've seen this message, but I'm not sure what's happening. Like whenever we install Java, it's still like 3 billion devices running Java. So it's just someone's being lazy there, or Java's market share not increasing. I'm not sure what. But then before going into all of that, can we get a more relatable example that helps us relate to this problem that we're trying, or the solution that we're trying to pitch, maybe?
Okay, so I would say like driving can be used as a very good abstraction here. So while driving, we have to know like which gear to take when we are going uphill, right? To make the most efficient use of it. Similarly, if there is a certain sound coming from the car, we will know by our experience that, okay, maybe the rear door is not locked properly. And therefore, by knowing all these internal details a bit, we are able to utilize the car more efficiently, and we are enjoying while we are having the ride. Similarly, if we understand the internals of the JVM, we can have a bit more efficient code, and we can find out more problems when they come. For instance, we have this file hs_error_pid, which is the process ID. And whenever there is any error, we get this JVM dump of the heap and the thread, right? So if we understand this fact, maybe we can go and find out what the problem was, or we can avoid the problem from the next case, whenever it occurs in the future, right? To actually make a major impact and to actually save our oceans, we have to first understand how does the languages work.
Right. So how does it run? In fact, it's we've been writing a lot of languages, and there's like an explosion of things, and that's how we seem to define ourselves nowadays. I am this developer, that developer. So broadly, we could categorize languages into two categories, them being interpreted and compiled. Interpreted languages like Python, Perl, Ruby, Lua, these kind of things, they offer a certain amount of abstraction to the programmer, giving them the benefit of not being too verbose and not being too imperative, and allowing us to write or declare what we want to do at an abstract level, and at the cost of running at a bit slower because all the work is done by the interpreter here, right? On the other hand, languages like Rust, Go, C++, etc. So these are compiled languages, meaning the code that you write gets compiled down to the thing that's actually running, the executable itself, right? So at times you would have to write a bit more verbose code compared to the interpreted languages, but then you gain on the performance because it's pretty much what the machine is what you're writing, right? So lesser abstraction, more speed. So that's kind of the trade-off that we have. So to understand this thing a bit more, let's look at what the JVM is doing. And here, I think I'm looking at Java and Scala here, right?
Yes, so there are two programs, both trying to print hello world. The first one is in Java, the other one is in Scala. And we can use the Java C or Scala C compilers respectively, and we'll get the bytecode, which you can see on the screen. On the left side, we have Java, and right side, we have the bytecode for Scala, and both print the output as hello world.
Right. So I saw some high level code Java Scala that looks more like code, but I didn't see any assembly here. But instead, I saw like an intermediate thing, bytecode, that I guess a lot of people know about. But is this compiled or interpreted, or which is better? I want to say yes, I guess.
Yes, to understand how does the JVM internally works to change your code to assembly, we have to first understand something. This is called hot code. Now, what is exactly hot code? So basically, hot code is something which is being used a lot again and again. And to understand this, there are some examples. Some loops which have more than 10,000 iterations, or some interpreted methods which have 200 invocations. There can be some partially compiled methods which have more than 5,000 invocations, or some tiny methods with frequent invocations. So basically, the idea is what we are trying to do. We are trying to have code which is called again and again, call it hot. And now you'll see as we go further how we can actually change this hot code and compile it, focus on it more and compile it to make it faster and therefore have way more efficient code, right?
Right. So I think we have a more human way of explaining this, let's say, right?
Yes. So we know that pictures are worth 1,000 words, but let's try to do a bit of a theater here to have it in million words, right? So here we have two characters. I'll be the interpreter because I'm very, very smart. And Rahul, you will be?
I guess I'm the dumb compiler here. I work very hard.
Yes.
But I'm not very smart.
Yeah, so Rahul is pretty hardworking, and therefore he will be working. He will be portraying the compiler. So let's say I have a code base. Okay, so these are line number 1 to 4, and can you please make the assembly for it?
Okay, I mean, it's good, but you haven't given me any like profiling information or something to work upon. So I guess this is the best I can do.
Okay, yeah. So let's do line number 5 to 8. And this time I'm giving you some more profiling information.
Okay, this is a bit better, but yeah, it takes a few more amount of time, but yeah, I mean, there you go. That's the best code that I can.
Okay, so, okay, then I'll give you line number 9 to 12 now, and I have more profiling information, so you can do this.
That looks good. Here's some assembly for you, but I think it's hitting my limits. And anything more than that, you have to go talk to someone more powerful.
Okay, so next one, I have line numbers 13 to 16. And now this time I'm giving you some information. Take all the time you need. But this is the code which is pretty hot, and I want it as much optimized as you can. So take all your time and give me the summary, please.
Okay, so I guess now I'm C2, right? So I have more time now. But yeah, I'll work on it. I'll let you know.
Are you done?
Don't rush me. You said I have all the time on the plan.
Okay. Are you done now?
Okay, here we go. But I think this is pretty good now.
Okay.
So,
so while you were working, I also got line number 3 to 7, and they have way more information, and maybe you can take some more time and give me more profiled, more optimized assembly.
Okay, and also I noticed that I've seen some of it before, so I have cached some stuff, so I wouldn't be as slow this time, right? Okay, so here we go. That's your assembly. Okay. Hope you're happy now. Smart pants.
Okay. Yes. So.
Yeah, we're back again.
Okay, so let's try to map this theater onto the C1 and the C2 compilers. So basically, the JVM is the best of both worlds, and it's a fusion. Therefore, it's called as a hotspot VM, or JVM's implementation is also called JIT, or just in time, because it's only compiled when it is needed, and it is made up of C1 and C2 compilers. So what happens is, the interpreter gets the bytecode and it uses the C1 and C2 compilers to change it into assembly. Interpreter does the profiling for performance, and C1 and C2 are tiered. So hot enough bytecode is sent to the C1 and C2, right? So the interpreter always keeps the track of the thresholds before the bytecode is sent to the next tier. And you can see some of the thresholds on the screen, right? So let's say I give, the interpreter gives code to C1 first with no profiling, and then there will be some code which it sends with limited profiling, or some it can send to C1 with full profiling. Now C1 gives back the assembly and it's moderately faster, but C2, given more time and good profiling information, it gives one of the most optimized code in the longer run, right? So notable examples of such tiered JIT are V8 powering the Chrome and the Node.js.
Right. That definitely makes a lot of sense. And I guess we can nail it even further down with something, hopefully that's more close to what we do on a daily basis, right? So fair warning, here with Dragons, we are in the depths of the JVM right now, right? I guess everyone here, or most of us here, probably are writing Java professionally or not, so, or some JVM language, and this is kind of relatable. Like, it is like a horrible nested for loop, and people who have gone through FANG interviews might know, like, let's not write loops like this. But that's irrelevant here. So why are we writing loop like this? That's not a thing. But it's a very contrived example here to demonstrate some of the things that we're trying to talk about. The purple bit here, the inner loop, that keep that in mind. And also, if you can see, the stuff happening inside is kind of constant. And like, do we really have to run that thing 100,000 times, right? So, and that has no relation with the variable I, right? So there's some obvious optimizations that we can do here, right? So given this loop, so when we pass it through Java C, right? Because we wrote Java or Scala or Clojure, whatever compiler you're using, you're going to get a bytecode like this. And don't worry about the details, what's happening here. Just notice about the jump instructions. The jumps have this CMP GE, means compare greater than equal to. So these are like jump ones. And here is where, say, we're comparing this. And so we do a compare and then we do ourselves. So essentially what this thing is this is where the outer loop starts, inner loop starts, the logic here, inner and outer loop again. So you might be asking, like, okay, that's fine. That's bytecode. We know how bytecode works, but nothing really changed in the efficiency. It was crappy for loop. Now it's crappy bytecode. So what we did essentially is bring it down to a level now which can be understood by any JVM regardless of the architecture. Right? So that's the right one runs anywhere, right? But we haven't done any optimization. The interpreter compiler dance that you saw, that hasn't started yet. Right? So now that we give it to the JVM, the smart interpreter runs through all of this and applies all of these levels of optimizations, like what's happening, what not. So profiling information. It has figured out that it has crossed the 10,000 invocation limit. So let's not get too smart right now. We have profiled that this is more than 10,000. So let's give it to C1. C1 is the first level compiler, which is fast, like Anu described, but it doesn't do much. It doesn't try to be too smart, right? Because whenever you're too smart, you're going to be slow, right? So let's try to get it out to assembly as soon as possible. Here is x86 64-bit assembly on Intel processors. So this is an sample output of what a C1 might do. And given the basic profiling information, again, details not important, but you see the same structure again. Outer loop, inner loop, logic, and then close the loops, right? So again, not much improvement there in that crappy for loop. So, but we already gained some speed improvements, right? So we are out of the interpreter now, or the interpreter doing things. We are directly running on the CPU now. So this is the just-in-time compilation system that JVM has been perfecting for the last 30 whatever years, right? But now, smart compiler figured out, oh, this inner block is kind of constant. We don't have to do that thing every time, right? So let's hand it over to C2 now. This is again an approximation of what C2 might do. Details not important. Important, but there's just one loop now, right? The inner stuff has been pulled out and it's able to optimize it in a single loop, right? So this, given enough information, enough time, the JVM is smart enough to do all of this, right? So at the end of the day, the output that the JVM has is quite amazing, and it'll bundle in all those years of research into the Hotspot compilation system, right? So given all of this, we want to take a bit of a pause here, and we realize that this is quite a lot of information. Do we have any questions till now? Especially this C1, C2 dance. It's quite a deep part of the JVM, but we think it's quite important.
We don't have any questions so far. Everybody following, don't be shy. If anything is not clear, just ask.
Right. Also, let us know if you're going a bit too fast, or we can tone down, tune the speed as well. Right.
I guess I could follow, but let's ask the audience. If anybody feels that we need to slow down, again, use the chat. Feel free, we can slow down. Yeah. Could you maybe explain the last part again? Jules is asking.
Last part, the C2, I suppose, right? So, yeah. Right. So if you remember what Anu and I was doing, like Anu is the interpreter here who's looking at how the code is running, right? So it says, oh, here is a loop, here is a comparison, here is a method call, right? So at various points in time, the interpreter is making a note of what's happening in your code, right? So that's the warm-up phase. We can talk more about the warm-up later on as well. Like it's when the system is figuring out how your code is running so that it can optimize it even further, right? And that's the magic of the JVM or just-in-time compilers, that it doesn't have to know everything upfront. It can measure the stuff as it's running, right? So given this, as you run measurement, it has figured out that the inner loop that you saw there, so the inner loop here, inner loop, it doesn't depend on anything of the outer loop, right? So that bit of computation could be cached once and multiplied, for example, right, by the times in the outer loop, right? So a complicated procedure called constant folding happens, and it's one of these optimization steps. Most of the compilers implement it, but the JVM implements it in a way that it can be done at runtime, right? And that's the smartness here. So C2, which is the smart compiler, but the longest time taking compiler, gets this bunch of information like bytecodes, and then says that, okay, oh, here is where I can constant fold. Here is where is happening because of the profiling information from the interpreter, right? It has marked all of these places, right? So that's how 2 parts or 3 parts of the system are helping each other, right? So it's quite a complicated dance there, but then you should arrive at a much efficient code at the end of it. Hopefully that was clear. You're muted.
Sorry about that.
Yeah.
I tend to do that. If you could observe like profiling at very low level, would you actually see this pause where C2 is kicking in and slowing, compiling, and then restarting again? Can you observe?
So yes, you should be able to pass these flags. The JVM takes a bazillion flags. I've lost count of how many options that you can send it. But then you can always ask the JVM to say, dump your profiling or dump your C2 stuff or dump your these things. So it's gonna help you along, and it's a marvelous piece of engineering. So you should be able to introspect it at I think there's more stuff about how to introspect later on. So Anu has some things on that. You don't have to like dig in so much into it, but there are ways to do it as well.
Okay, thank you. Jules, let us know if that was clear enough or if you need further explanations.
There's too many things on my screen.
Yeah, please.
All right, so now that we know that we have all of this machinery, what effect does it have in real life?
So one thing which we have to be very, very careful about is, though it is great that we are having so highly optimized code and like the machine is learning on its own, what happens when there is a de-optimization, right? Because like it has optimized to a lot of level and it has to come back all the way, right? So as you can see with the diagram, that these penalties can be as heavy as 100 times, right? So what are the reasons when these penalties can come in, right? So if let's say the interpreter made some assumptions in profiling, or if there was an uncaught exception which was thrown, or maybe the best example, which everyone would remember from now on, is reflection, right? Because we have to actually go back and like understand what was happening to get to where we are, right? So now, therefore, we say that exceptions should not be used as a control flow, and reflection should never be used, should be avoided as much as possible.
Right. So I think is this why like 30 years of abuse we have been suffering from these other people, like, oh, Java is too slow, especially this .NET set of people.
Right. So I would say like, if we are just micro benchmarking in the very beginning, right? So the startup time has some penalty, but given enough time, JVM can actually optimize code way efficient than anyone else, right? So I wouldn't take the whole blame. I would say just let's optimize it end to end.
Okay. I mean, I think this is a very nice choice that the engineers had made there. And I think it works out pretty well now, right? But then a lot of us have seen Java being called as legacy code, right? I guess Anu has a lot of baggage that she carries from all the banks, I suppose. And then, but then if you imagine the code that runs all the legacy code is probably even more legacy, right? So C1, C2, these are like fantastic pieces of code, but then they have their maintenance baggage. They are written in quite old tooling and keeping it compatible with a lot of CPUs. So that is quite a set of maintenance. And given the kind of things that they're written in, it's quite a task to maintain them and upgrade them and add more features to it, right? So there's always a lot of research happening, especially in compilers and optimization. So is there a way to ease this upgrade pain and maintenance pain, right? So to quote Cliff Click, one of the creators of the Hotspot JIT. So the thing that we're talking about is the hotspot. If you think about it, it kind of makes sense. The interpreter is finding the hotspot and then trying to optimize it. Right? He says, among other things, I will never write another VM in C and C++ again. It's too much pain. Right? So this is unmanaged memory. I have to think about a lot of stuff. But then we could do something better here. Right? So how can we actually help the future generations? Like, so not only they should be able to see the flora and fauna that Anu was talking about, but also innovate and add more features and brighter young minds writing more better algorithms later on, right? So for that, since JDK 9, we have or JVM, the 9th release of the JVM, we have broken it down again into smaller composable pieces. As we all know, like breaking down things is nice, #microservices. We have broken it down to have a compiler interface among the other things. So it's called the JVM CI, JVM compiler interface, which means that I can plug in my just-in-time implementation now. It doesn't have to be C2 anymore, right? So essentially what the JVM CI does is takes in set of bytecodes, byte array pretty much, and gives you back. So anything that takes a byte array, gives back assembly, can be plugged in here, right? So now you have this mechanism to write better things, and not necessarily in C++ and not necessarily in the JVM, right? So now that we have it, what does the future have for us?
So one of the things that we have is GraalVM. So it was made as a separate project for enhancing the efficiency for the JVM, right? So initially everything was written in C and C++, and therefore it was very difficult for people to write more efficient and complex algorithms, right? So Graal project did the replacement of C2 by Java. So now people can write more complex algorithms to enhance the C2 compiler. Right, so the GraalVM had some superpowers. So one of them is Truffle. So Truffle is a framework or a set of APIs to parse the language. So let's say if there is a new language, we will tell the JVM how to create the abstract syntax tree using Truffle. And Polyglot is a framework by Graal to load and interop between them. So if it is enabled, it helps in switching of the languages when running. So another one is native image. So native image is ahead of the time compilation for Java bytecode from any JVM languages to a standalone executable. So instead of compiling it at the very end, we'll make the whole compilation at the beginning.
Right. So isn't that the solution to, again, the 30 years of abuse? Like, let's all compile Java and then never have the startup time problems, right?
Yeah, so I would say like it's about whether you want to use a knife or a sword to cut butter, right? So let's say if we have something such as linting or AWS Lambda, right? So these are the things which will need Graal. So it will consume a lot of energy at the beginning. And when I say lot, it's a lot. Use it on your computer, you'll understand what the lot means, right? So it'll stop. And therefore we avoided it in the demo, because when we practice it, it stopped my system. But then if we have something as a server of a bank or something which is running over a long course of time, no one can beat the current JVM, right? It will give one of the most optimized code in the longer run, right?
Right. Yeah, but yeah, I mean, I'll just want to add, like, GraalVM has improved, so we can all go to do like more and more releases. So hopefully the startup time is not, compilation time is not as bad. But yeah, but every time we go look at GraalVM, they have made much and more improvements, right? So continuing on innovations, Project Loom, something that I'm personally very looking forward to. A lot of us might have known that concurrency is hard. It's probably harder on the threading model that Java has, and I don't know how much of us actually write concurrent Java code. And there's some brave people among us as well, right? So to not to simplify the difficulty of it, but to increase the concurrency aspects of the JVM. Project Loom brings in the ability to have this thing called as a virtual thread, meaning it's a lighter weight construct compared to a real OS thread, so that you can have multiple or like thousands and millions of them running on few OS threads. Right? So most of the time you see, we just wait on the network to do something or wait on the database. Right? So that doesn't need your CPU, right? So if you want to wait in parallel, you can go do that on a virtual thread, right? And you can do lots of them now. Right? This has already landed on the mainline JDK source code. You can see the commit, massive, huge honking commit. And it's available on early access previews from JDK 19. I'm hoping it's out as preview on JDK 19, right? So this is simplify a lot of stuff, a lot of the way we think about concurrency, right? In general. Project Valhalla, a lot of projects coming in, right? So this is about reifying the generics. By reify, I mean like, imagine you have an array list of integers, and then you're thinking, it's just an array of ints, right? So I'm wasting so much space of having an object wrapper around boxed types, right? So if you have a thing like that, it gives you a lot of advantages there, right? You can say .add, find, you have a lot of helper methods if it's an object, not a primitive type, right? But you should be able to use it like that, but it should run as a primitive type because that's where the performance is, right? If you don't have too much layering between your code and the things, so as we learn, if you compile more and more. So Valhalla is about flattening this object hierarchy that we have. Think of it as it behaves like an object. You use it like an object, but it runs like a primitive data type. So that's a very fascinating thing Project Valhalla is doing, right? But this, for example, is already implemented on .NET runtime. So they are like a bit ahead here. So JVM's catching up. Panama is about simplifying the interop story that we have. If you want to talk to something that's outside the JVM, right? And you want to, for example, a native module, right? If you want to do machine learning on the JVM. So that's why Python is so famous, right? Because its interop capabilities with C native libraries is very nice, right? So Panama would improve that over JNI, Java native interface. Panama makes it a much more simpler story there. We can finally do machine learning on the JVM now, right? But then historically, we've been seeing whenever humankind has innovated, there is a lot of garbage produced, right? And we conveniently forget about it, right? So we just like have our candy, throw the wrapper away, right? And then be happy with it, right? So what can we do about all the garbage that we produce while innovating?
So I would say like we are heating up the oceans and also we are creating so much garbage for the oceans. And I think since we can't stop creating the garbage, right, in both the places, we need a robot. And at least for the JVM, we have one, right? So what happened in 90s, the memory was short and therefore the garbage collection became mainstream. Though the machines can now handle it much better, but still we have the garbage collection, which was already in place, right? So let's try to have a look at a classic garbage collection algorithm called mark sweep. To understand mark sweep, we have to first understand what is reference counting. So there is a heap of memory and there are locations in this heap. And each memory location is called by some number. And let's say that for now, for the sake of this example, we have this heap location called A, right? So this is a memory where there will be some variable, some value stored. So reference counting is basically the number of variables which are pointing to this location. So let's say we have 5 variables pointing location A and then 3 variables pointing location C, then these are actually the reference count for those respective locations, right? So now mark sweep occurs in 2 ways. The first is mark, right? So in this, what happens is the mark goes to every location and it counts the reference for all of these locations. The second phase is sweep. And in sweep, what happens is all the places, all the memory locations where the reference count is 0, these are freed, right? When the sweep occurs, the entire heap is frozen, and this is known as a GC pause or stop the world GC, right? So now, to try to solve this problem, what we had to do was we had to reduce the pauses to parts of the heap. And a statistical observation was made that most objects die young. So what we did was we had this structure of the heap where there would be Eden, where all the new objects would be created. And after a certain time, whatever objects survive, they will be moved to S0. After some time, they will be moved from S0 to S1. And then after some more time to tenured, and then after some more time to permanent, right? So whatever survived the GC cycle, that moved forward. And this was known as the generational memory model. So now parts of the heap and parts of the JVM were getting frozen. And tenured was having less, and permanent was having almost no GC pauses, right? So static variables started in the permanent generation. So maybe, Rahul, we can share about some of the newer upcoming GC innovations in the JVM.
Right. So how many of us knew that there are more than one garbage collector in the JVM, right? So as it is with the rest of the JVM, here also there's a lot of innovation going on. G1, G stands for the generational thing that we learned right now. So that's it's still the default garbage collector, but that since JDK 7, that implements this generational fragmented heap that we can collect at different intervals, right? Since JDK 11, we have another thing called ZGC, which is a different option or like a different kind of a target that it has. I'll cover ZGC a bit more. Shenandoah, since JDK 14, is specially crafted for targeting huge heaps. So it's 2022, and we have machines with terabyte heaps, and people use them. So our garbage collection performance shouldn't scale like exponentially. The amount of memory that we have or amount of heap that we're targeting, it should be at worst linear, right? If not even better, right? So Shenandoah is made for these larger, massive heaps, and also try to fragment the pauses even more and reduce pauses even. Special mention to ZGC, since JDK 16, it guarantees a pause time of less than 1 millisecond, no matter the size of the heap. And that's an extremely amazing guarantee that it has. And this can enable a whole different breed of applications running on the JVM, right? So if you are having a lot of thrashing, a lot of paging ins and outs of the memory, ZGC is something that you should consider if you're doing high frequency trading, like half the London population, right? So, but I am a sane person. I don't want to go so much deep into it. I just want to shut down the laptop at 5 p.m. and then that's it. So is there an easier way to keep track of these things? Like, do I really have to go with my profiler everywhere?
So for as lazy people as you, we have something which is called the Java Flight Recorder. So it gives the in detail atomic view of things. And recently it has open sourced as well. So it's a tool to understand the performance of the JVM in a very visual way. And there are other such tools as well. One is a visual VM, right? And let's say if you are on cloud, then we have JFR Metrics for dashboards as well on these clouds. So you can use them.
Yeah, okay. That at least satisfies my day-to-day job of running after people who eat up too much of my allocated containers, right? So, but what am I getting here? Like, is it, you're saying that I have my shitty Java performance, but then I move these tiny bits around and then suddenly everything is good, is it?
So I learned this in the beautiful city of Hamburg, that small tugboats can change the direction of huge ships. So if we all do a bit, we definitely can make maybe half a degree change to the heats that we are doing and save the oceans.
Hopefully our problems are not as big as the Ever Given ship here, which blocked the whole of Suez Canal. So but still there's a solution to it. Good to know. Okay. Lot of information, lot of things, but can we condense it down to some takeaway points? If not, if you couldn't remember most of our talk, but at least hopefully we can give you something that you can take back. As I said in the beginning, weren't too much details. So just joking there. So just static blocks, static initializers and variables. So these something that we learned there in the fragmented generational memory model. Like they start in the permanent gen, and if you have a lot of them, they're gonna create a bunch of GC pressure, right? So that's what we learned. So be wary of, or be judiciously use static stuff, right? Or like don't have too much weight on them. ZGC is available now. If you're thinking the JVM pause is gonna kill you for your applications, a lot of JVM gets a lot of flack for its GC pauses. Try out the ZGC, right? Native image, part of GraalVM, that is gonna enable you instant startup time or consistent startup time. And if you're running lambdas, if you're running command line tools, if you're running linters, consider the native image of GraalVM. So that has its benefits as well. And you still get a natively compiled managed memory thing, right? So yeah, and finally, all of this is irrelevant if you are measuring the wrong thing, right? So you're going to see a lot of benchmarks online. You're going to see, oh, this Java is bad because it couldn't calculate the 50,000 Fibonacci number correctly. I mean, that's not something that we do in real life. Right? So those are micro benchmarks. Those are things that a lot of people use it for various reasons, but that might not be what the real life is. So measure the right things. Don't trust the micro benchmarks. Whenever you see there's something that could be sped up or something that's too slow, it's probably an IO thing going on there. So it may not be your code that's at fault. So profile these things, find these things out. Also know that the JVM is there with its smarter interpreter, dumber compiler combination to figure that out as well, right? So given all of that, we hope that we can all know how the JVM works. We can write a bit more efficient code. We can help it along as well and produce less heat, if that's the takeaway that we want to do, right? So our machines get less hot. Our laptops don't heat up our room this summer, right? And we can keep our earth green and blue, like with our friend here, Luca. I'd like to end here, and hopefully you had some useful points to take away from this. Too much detailed talk. And we are open for questions. Thank you.
Thank you, Rahul. Thank you, Anupriya. I don't see any questions right now. Mm-hmm. Let me have a look at the chat as well. No. There was a lot of content. I really liked it. There are no questions. I have one. Curious. As you said, the ZGC doesn't hit with big pauses, right? I mean, it can guarantee lower than 1 millisecond. Is that a reason why this is not the default? Where does it not shine?
So if I can think of a possible reason, it could be. So one of the things that I can tell right now, Java doesn't want to break existing things. So that's a guarantee that all the JVM developers try to keep like 30 years backwards compatible. That's another deal that to do. So if you're changing the default GC, and who knows what people are doing in the Java code, they could be relying on that. So if you change the default one to another thing, and probably there is something that's breaking there. And one of the interesting bits that happened since JDK 16 is this thing called strong encapsulation of the internals. So that did break a bunch of things. JVM did not allow you to like tap into parts of the compiler anymore, right? So one of the examples there is, what's the library called again? Lombok, if you know what Lombok is. So that hooks into the Java compilation process and then does its thing, and it pretty much doesn't work since JDK 16. So that's so I would assume like that's a reason that they wouldn't want to switch the default garbage collector to
the risk that it might
ZGC.
break. Yeah.
So that could be one of the things, and I think ZGC takes a bit. So it's not as general. So the reason that it can guarantee the pause time, it's not in the same way generational as G1 and Shenandoah are. So that's why it has like a big view of things, so that it can guarantee a more consistent pause time. So if you are in a heap state, which is massive, like Anu was saying, right? Like if you're lot of thrashing around here and there, so ZGC might not be a good thing here. So if you're like a 5 terabyte heap, so there's, whenever someone has sold you a big marketing claim, 1 millisecond passing. So there is a caveat somewhere.
Accounted for, yes, yeah,
yeah, terms and conditions. Yeah.
Any more questions coming from the audience? Don't be shy. There are no silly questions. I usually make them, so no worries.
I definitely realize we ran this longer than expected, but yeah.
Oh, I think it's still okay. Just one minor heads up. There's a lot of content. We will be sharing, hopefully, the slides. So take your time if you want to review that. We will send probably an email tomorrow. If there are no more questions, I will hand it to Matteo for the final thoughts.
Yes, first of all, thank again, Rahul and Anupriya. I just want to share a couple of information before we close the session. And I'm gonna help myself with a couple of slides. So the first one is a teaser of the next event, which is gonna be titled Test-Driven Development with Terraform, held by Amit Dubey, and this will take place on the 23rd of June, of course, this year. Further communication will be sent out on the usual channels, but this is already official, so in case, save the date. And the last thing I also wanted to mention is that a feedback form will be sent out as usual. So we're really interested to get your feedback on any aspects of the session, so we can continuously improve and make sure that the next sessions are even better than the previous one. And with that said, I guess
can I jump in? No, just sorry.
Sure.
We do have another question, if that's okay, folks.
Okay.
Samson is asking, when do you think is a good time to try a different garbage collector? Interesting.
Right. So do you want to take it or no? Or
so I would say I think people are just having some hiccups. So I'm working with one of the major clients in ThoughtWorks, and we were talking about this, and it's just that they want to benchmark it in the longer run, like sample set and check out. But the thing is that the tech stories never gets prioritized, right? So you have to actually market it in a way where you're like, okay, you're using this and you're getting this in return. So people do not feel the need. So once the market is created, yes. And I think where the people such as trading, if they want to use it, they are very specific. Only once, like people who are not so sensitive on time, once they check it, and then they will go for it. So it's the same chicken and egg problem. So it's more of the marketing thing. And yes, we will get there with time, but I don't think so technology wise, we will only get better like the JVM C1 and C2, right? So the more you give, the next time you will have better from there, right? So, okay, I know cycling, I do more cycling, I get better at that. So it's the same thing. So I can't think of any other reason except these. Rahul, what do you say?
Yeah, I'll just add on to this saying, like, it's the measuring problem again. So there is a reason G1 is still the default. and if you are seeing like there is something that's slowing you down, or so again, like before doing any of these things, make sure you have enough profiling, enough measurements, enough metrics that you're emitting out of the JVM, and try to narrow the thing down to a place that, okay, that's why the GC pauses. So I can give an example of my current workplace, which runs one of the largest Elasticsearch clusters. Elasticsearch, for people who don't know, it's a free text search engine, which is primarily in Java, open source, massive heap. So we run about 35 machines, 128 gigs of RAM each, right? So that's about a 50 terabyte working set, right? And that has its GC pause. And then we're still on the G1 garbage collector, right? But again, we put in all these checks in place, and then we figured out why are we seeing so much GC pauses? Because the query that's coming in that needs to be searched, that's massive. So we solved the problem by limiting the amount of things in the query and not changing the garbage collector. So try these things first, because that's probably the problem is where these things are, not the platform, right? And if you still think that, okay, I would using ZGC Shenandoah, so ZGC and Shenandoah, these two are primarily for what ZGC is for like extremely low pause times, but the caveat is you can't have humongous heaps, and you're gonna see fragmented things there. And I believe there's a feature of ZGC being kind of generational, but I'm not sure. Shenandoah is for humongous heaps, but it's less battle tested. It's less, how do you say? I'm not sure about the generational story there, but again, like if you're not running a 40 terabyte heap, probably not worth it. And I'm not sure how many of us run a 40 terabyte heap. So yeah, measure these things first. And also what Anu said is important, like getting this thing green flagged by your product manager engineering thing is I definitely the bigger problem. You're not.
You wouldn't even get the time to say, okay, fine, I have micro benchmark this with this and like long benchmark with this and this. And to get that spike in, right, they'll be like, why? What's happening? So to explain, and then to the business, like, so when you're talking about the JVM, right? So if you're saying I'm going to change this flag, you know how many people are going to come down at your desk and say, what? Have you gone crazy? Because most of the people don't even know about like these things exist, right? And how many people do change it, especially when things are running. And that too, it's useful when things are quite critical, time sensitive or huge. And at all the things, people won't let you change unless and until there is no other option. So I think it's more of a people problem to start getting used to this and the scenarios as well, right? So do you have a small place where you want faster times? And is it starting where we can start as soon as possible? Can we test it, right? Without going down for more than whatever the standard time is. So
I know there are more consultants in the call as well, so they might have other experiences.
Happy to listen to those if anyone has, right? Yeah. So
we will be there. There's another question, if I may.
Sure.
Somebody anonymous, but still valuable. As we discussed, innovation is constantly happening in the Java world. So the question is, should we keep our JVM updated to the latest version as best practice? Also thinking that, as you were saying, something innovating is not turned on by default, right? So what is your point on this?
How's the client story with you, Anu?
So I would say we have to be aware. That is very, very important. And all these things that are happening, they're happening in labs and in schools and people who are actually not delivering new features. I'm one of those who's delivering. So one thing which is very, very important, and I would again say thanks to ThoughtBooks for giving me this platform where I got this urge to be aware, right? Once you are aware, and then we all as engineers can see, okay, what are the things which can be helpful? And maybe when you get that personal development time or that urge of like, no, I can make better, put your couple of hours, 4 hours, after that awareness, like, can it make a difference? If you can show people, right? If you can show numbers to anyone, definitely, you can make, you should go. And then also, right, you have to see that is the update, like if you're benchmarking something, right, and you see there is a high difference, and then you have to associate the cost. We engineers forget that part. Is it worth the cost of, because there is an update, things might not be stable, and what can go wrong? So we have to be very, very careful that we understand the business language, the business does not understand our language. So first is to be aware of everything. Then is, if we think, if we can prove to our fellow engineers why this has to be done, and if we have those numbers, present it, there are people who are listening. And now the awareness in the industry, in the business, has also gone up for engineering, right? Because it was just time, right? They were waiting, and now people are listening. So if you can go with numbers, yes, it's worth it. Let's update, go for it. But just not being aware will not help you. And going without numbers, in my experience, has never, ever, ever helped me. So anything more to add, Rahul?
From the infrastructure side, what helps driving these things is looking at critical vulnerability and exploits, CVEs, and Java being Java, used by half the planet. So there's going to be some vulnerabilities, there's going to be some issues coming up. So if there's such a thing, then you should definitely upgrade. You should prioritize it over other things. This is my personal paranoid infrastructure consultant talking here. But the other thing that I've seen work is going with LTS, long-term support versions. So if you are a business who cares more about the delivery bit, or like is very user-facing, so they don't care which JVM version you're running, but that's like a very engineering thing to be proud about. We are on the latest. Okay. But if you're tracking the LTS, it could be a safe bet there. And also I want to add that Oracle has switched to a 6-month LTS cadence, not LTS, sorry, release cadence. So every 6 months there is a new version of the JVM, which is like amazing compared to what it was. And every 2 years there is going to be an LTS release, long-term support release. So if you target the LTSs, they not only backport security fixes, but they also improve certain things that they think that later on something nice came up, and then so these kind of things. And the other thing that also might help you is with this new release mechanism, 6-month release mechanism. Whenever there's a new feature that's getting released, like Project Loom, for example, or Java 14, you have this JVM Java records, which is like an immutable way of doing things, right? So whenever such a thing comes up, it'll be released as a preview release. We'll say preview, second preview, and maybe in the third preview it's stable or it's gone, right? So there is a way to test these things out. So if you're looking forward to something, just deploy that piece of code, knowing that it might not be there, right? So track the preview releases, track these things, and yeah, again, if you can make a case for it, yes. But again, all of this aside, there's security updates and then there's feature updates. So yeah, that takes priority.
So I would say, like, what I spoke about was more about, like, let's say if you want to change a flag, or do you want to change or upgrade your garbage collector. But I think what Rahul is talking about, like, just the general updates, right, for the JVM. So I think you got both the answers. So whichever you were looking for.
Thank you very much for the practical suggestions. they're very relatable to what we do. So sorry Matteo was saying thank you and I stopped him. So we'll thank you all once again. Thank you to our speakers. That was super interesting. And thank you for the audience. We will share the feedback form and the content, the slide deck with you in the next days. Make sure you follow the next events, and have a good evening, everyone. Bye-bye.
Bye-bye.
Bye-bye. Thank you.